Hi, what I have here on the workbench today is an OWON HDS272S handheld oscilloscope. This is a 3-in-1 device which has a dual-channel oscilloscope, a multimeter, and the S version also has a single-channel arbitrary waveform generator built in. Banggood sent me this unit for a review, and I'm very excited about it because, if you recall, I had reviewed a similar unit, the Handheld 2D72, not too long ago, and that unit has very similar specs compared to this one, and quite a few of my viewers wanted me to take a look at the OWON HDS272S and see how it compares to the Handheld 2D72. For this video though, I'm going to concentrate on reviewing the OWON HDS272S, as there are a lot of areas I wanted to cover and I don't want to make this video too long. And I'm planning on a side-by-side comparison video between this oscilloscope and the Handheld 2D72 in the near future. So be sure to subscribe to the channel so that you will be notified when that video comes out. For those who wanted to buy one or just to check out the HDS272S after watching this video, you can follow the link I included in the video description below. As I mentioned in my previous videos, handheld oscilloscopes can be quite useful in a lot of situations because the scope itself is not mains earth referenced. This means you can do a lot of measurements without having to worry about creating some spectacular shorts when measuring mains earth referenced circuits. This could happen with a benchtop oscilloscope if you are not careful, as the BNC connectors on a bench oscilloscope are mains earth referenced. So if your circuit under test is not fully isolated, and if you accidentally hooked a ground clip on a live wire, you could potentially cause a lot of damage. The OWON HDS200 series has two bandwidth choices. There is the 242 model, which is the 40 MHz version, and the 272 model, which is the 70 MHz version. The versions with an S at the end also have built-in arbitrary waveform generators. To me, if you are getting one of these, it is well worth the extra $30 to get a version with the built-in arbitrary waveform generator, as it can come in quite handy in a lot of situations. The unit comes in with a soft carrying case, and you do get all the accessories that you would expect. It has two of these BNC to alligator clips and a set of multimeter probes as well. You only get one set of these oscilloscope probe, however. You will have to supply your own extra probe if you are planning on doing dual channel measurements. And that was pretty much the same as what came with the Handheld 2D72 as well. Now, keep in mind that the OWON HDS200 series competes directly against the Handheld 2000 series. So you will see that the price and functionality-wise, they are very similar, but OWON tries to outspec the Handheld in pretty much every single aspect. And you will see that later on when I do a side-by-side comparison in a separate video. Okay, enough said. Let's power it on and take a quick look. Wow, that is very quick and quite impressive. As you saw, it turned on almost instantaneously. This is actually very important in my opinion, as a lot of modern test equipment takes tens of seconds to just boot up. And for a held device like this, that would almost be unusable. So certainly hats off to the engineers and designers at OWON for this. Let's take a quick look at using the enclosed oscilloscope probe. And the probe supply is an OWON 3070, which is rated for 70 MHz bandwidth. So let's plug it in here. And this OWON unit has also a probe calibration signal output on the side. So I'll show you if I can open it. As you can see, we have the test signal output from here. And this is the ground. This is the charging port. And let's hook it up and take a look at our oscilloscope probe here. So we can already see a signal coming out. Let's auto-acquire it. And the probe actually compensation is not that bad. It's almost perfect. So let's just adjust a little bit. And that should be it. Like the Handheld unit we reviewed last time, this OWON also remembers all the settings you changed, so that when you power it back on, it will go back to where you left it off last time with all the adjustments you made, which is very convenient. So for instance, if we are changing to, let's say, the arbitrary waveform generator mode, and we power it on, and the power on you do have to hold it, and so let's turn it back on. It will go directly back to the arbitrary waveform generator mode. So that is very, very convenient. Now let me cycle it back to the oscilloscope mode. And by the way, I had played around this prior to this review, so right now this is not the factory default settings. And if you ever wanted to set it back to the factory default, just press the system button and press the default setting, and press it again. It will reset everything to the factory default, so which is very convenient here. Now I have hooked it up with my UTG 962E arbitrary waveform generator, so we can take a look at a few waveforms. But before I do that, let me just show you there's some very nice attention to details here. So if you look at these BNC connectors, the outside are insulated, unlike your typical BNC connectors. The outside here, you can see these are plastic shrouding here. And the reason for that is you routinely use the handheld oscilloscopes to measure circuits with a floating ground. So if these are actually not insulated, you could potentially touch it while you are doing some measurements, which causing a shocking hazard. So that clearly is a very nice attention to detail. Let me first turn off one of the channels, as we are only using one channel right now. So for that, I'm going to go to channel 1, 2, and if I press it again, it goes to channel 2. That's pretty intuitive, and I can switch it off. So now you can see that we only have the indicator for this channel 1, meaning that the only channel 1 is active. And you can see here we do have different, let's go back, channel. We have different probe selection here, and right now is at times 10, and this one is actually at times 1. So if we keep pressing it, we'll see probe times 100, 1000. So this is actually a little bit unusual. Usually you have, on the standard oscilloscope, you have times 1, times 10, times 100, and this one does have times 1000. And let's just go back here. And I think it has one more, times 10,000, which is even more unusual, which means that this probe can be used to measure some high voltage. Of course, you have to equip it with the correct oscilloscope probe. And let me just change it back to times 10 here. Now let me enable the output from the arbitrary waveform generator. And of course, the signal here is not triggered properly. Let me use the auto acquisition to try to capture the signal. Wow, that's actually pretty quick. And we did capture the very stable signal. Now, the amplitude, interestingly, is not full screen here. I'm not sure what the algorithm is, but let's try to adjust it to fill the screen here. Let's see, channel 2 is off. So let's change it back to channel 1. I think that's the issue here. Yeah, the user interface is not very intuitive here. So let's see, channel 1. Yep, so vertical scale using these two buttons, it did say that. So let's see, 5 volts, 10 volts, yeah. So see, I would have expected, at the very least, it defaults into this 5 volts range versus the 10 volts that we saw when we did auto acquisition. And you can see that the waveform is actually very, very stable. So let me try to increase the frequency. Let's do 60 megahertz, and let's change the horizontals. And you can see that the waveform thickened a little bit. So that tells me there's some jitter going on, and it depends on the algorithm of this scope. That's how they chose to display the final waveform. And on some scopes, you're probably going to see this sinusoidal waveform wiggle a little bit. But on this one, it's actually very stable, but it's just a little bit ever so slightly expanded. So let's now take a look at a square wave. Right now I'm outputting a 1 MHz square wave signal from the 962E, and let's automatically acquire the signal again. Again, the amplitude dropped back to the 10 volts range, so let me change it back to 5 volts. So let me see here. This is channel 2, channel 1, okay. Yep, So we can change it to 5 volts range, and let's try to expand the signal a little bit by reducing the time base here. And let's see the horizontal. So the time base is, yep, this button. Yeah, that's pretty good. And I can see that change between the different time bases is really instantaneous, very, very fast. Very good. The update rate of this scope is certainly very impressive. Right now I can see very fast flickering here. That's because the waveform is ever so slightly changing. And according to the spec, the waveform refresh rate is at 10,000 waveforms per second. That is very impressive. Of course, as you'd expect, this scope also has all the basic measuring capabilities as you would find in other digital scopes. So let's give it a try here. So let's do measurement. And I want to use cursor. And type. Let's see, channel 1 voltage. Let's do time. Let's try to measure what the frequency of this waveform is. Let's do time. And let's try to start at the beginning of the waveform here. That's good enough. Let's move the other one. How do I do that? I think I can press B. Yep. So now it gives you the AB is roughly, let's see, 1000 nanoseconds, which is very close to our 1 megahertz frequency that we are measuring right now. So if in fact this is a 1 microseconds, as you can see that's indeed the frequency we're currently outputting from the 962E. So let's take a look at other display functionalities we have here. For that, I'm going to change it to cursor here, I believe. By the way, this takes a lot of use too. At one point, I did not realize that I have to press this to go back to the main menu, and it took me a while to figure that out. But once I figure it out, it actually is not that bad. So for instance, right now we're doing the measurement. we're doing the measurement, and we can add what we want to measure. So let's say frequency, we want to do amplitude. Let's do the next page. Min, max, peak to peak, and min. Sure, so let's do that. So let's turn the measurement on, and you will see that the measurement now is being displayed. So that is really handy here. Of course, the VPP display right now is way off because we set the probe to times 10, whereas the output actually is just 2 volts peak to peak. As a dual-channel oscilloscope, you'd expect it to be able to display Lissajous figure by inputting signals into both of the channels. And now we're displaying in XY mode. The signal I'm putting in right now are at 5 kHz for both of the channels. So let me vary from, let's say, the input into channel 1, and we can see how the figure changes here. And you can see that this is really impressive how fast we are able to capture the waveform, given that this is a digital oscilloscope. In fact, a lot more expensive oscilloscopes cannot do the XY capture mode in this resolution and the speed that we're observing here. So I have to say I'm very, very impressed by the capability of this HDS272S, especially given its XY mode capability here. Now let's take a look at how well this oscilloscope displays modulated signal. For that, I'm going to output a 1 MHz signal at 1 volts peak to peak as the carrier signal, and on top of that, I'm going to do a 10 kHz amplitude modulation at 100% depth. So now let me enable channel 1 output, and let's do a automatic acquisition on the signal here. And now we can see the generated signal. Of course, to view it better, let's reduce the time base here. So let's and you can see we have the envelope of the modulation here. That's very nice. Now, actually, it's very stable as well. So actually, I don't know what is causing the display to be like this, but I assume, let's change the trigger point. I assume that we can probably make it trigger nicely. So this is just the artifact of it not being triggered properly here. So, but once the waveform is triggered, as you can see, we get a very stable output waveform, which is very impressive. And what we're seeing here is a frequency modulated signal. The carrier frequency is again at 1 MHz, and the frequency deviation here is 100 kHz with a modulation frequency of 80 kHz. What I'm going to do next is trying to verify the bandwidth of this oscilloscope. Now this scope is spec'd at 70 MHz, so right now I'm outputting a 0 dBm signal from my HP8642B at 50 MHz. So what I'm going to do is going to gradually increase the output frequency to see at what point we drop below the 3 dB line. First, of course, let's acquire that signal. And again, the automatic acquisition, for whatever reason, does not set the amplitude correctly, so let me manually adjust that. So for that, I'm going to change it to 2 volts per division. That's good enough. And I'm going to leave the horizontal the way it is. So right now, let me start increasing the frequency. And this is a 50. I'm going to increase to 75. So we already saw that amplitude dropping a little bit. So let's keep increasing that. So we drop it even more. Right now, let's just go straight to 100 megahertz. And at 100 megahertz, you can see that this is barely usable anymore. So let's go horizontal. Let's see. As you can see that we are actually, the signal is smeared quite a bit. So that tells me that there's some instability inside this oscilloscope, making the waveform actually spread out the way it is. Keep in mind that this scope has a maximum sampling rate of 250 megasamples per second for single channel operation, like what we're seeing here. And if you are enabling both channels, that sampling rate drops to 125 megasamples per second. So right now, even at 100 megahertz, we're really approaching the maximum limit that can be shown on this oscilloscope, regardless of what the bandwidth it is, because the maximum sampling rate is only at 250 megasamples per second. So let's try to increase the frequency a little more and see what we got. And you can see that right now it's 105 megahertz. That's just totally unusable now. So I would say the maximum usable frequency is not too much higher than the 75 megahertz that is specified. Here we have the 75 megahertz, and you can see the waveform is nice and clean, but as soon as we go to 100, the waveform becomes heavily distorted. And let's see if the built-in hardware and software can measure this 100 megahertz frequency or not. So for that, I'm going to, let's see how we did this before. Measurement on, and you can see we are actually not able to measure that frequency. So let me reduce the frequency range to see if we can measure that at a lower frequency here. So 80 megahertz, no problem. And let's see, 85. Yeah, so actually we are not able to measure that much higher than the maximum 70 megahertz specified frequency. It seems that 80 megahertz is the maximum that we can measure reliably. I'm going to show you the single-shot capability of this oscilloscope next, but before doing that, let me just show you how fast the waveform update rate really is. So right now I'm just connecting it to a switching power supply, and you can see that when output is enabled, of course, there's a lot of noise generated from the power supply, and you can see how fast the waveform update really is. This is actually very impressive for a handheld oscilloscope of this price range. As you can see, the power supply I'm using here is actually very noisy. Right now the output of the power supply is off, but you can still see the switching noise on this oscilloscope. Now I have set everything up so that we're ready to do the single capture here. So to show you what the setup is, you can see that the horizontal we're setting at 50 milliseconds per division, and the vertical we're setting at 2 volts per division. Now this is showing 20 because we have a times 10 probe, even though we're currently using time 1. So that should be able to give us enough room to capture the signal. And if you look at the trigger here, the trigger level is right above the 0 DC line, so that we can get rid of the noise. Otherwise, it will be triggered immediately whenever we turn on the single shot. So now everything is ready. Let me turn on the output from the power supply. And you can see that we have captured the signal without any issues. And by the way, the memory depth of this scope can also be configured at either 4K or 8K. So if you take a look at the horizontal menu, you will see that we have a record length. Here by default is set to 4K, and we should be able to change it. Okay, we can change it when the operation is stopped, so let's re-enable it. But if we wanted to capture as 8K, then we certainly can do that. And in this case, the captured waveform is largely the same, but it nevertheless has a little bit more resolution. And for example, if I just re-enable the output again, you will see that we indeed have captured this waveform now is with 8K sample depth. Now let's take a look at the included digital multimeter. The multimeter included in this OWON device is rated at 20,000 readings, which is really impressive considering that this is a 3-in-1 device. So let me put it through some tests to see whether or not we can rely on this multimeter for our everyday measurements. And right now we're in the millivolt measurement mode. You can use this switch to switch between volts and millivolts. And for that, I'm going to output a voltage from my EDC voltage standard. Let's see if we can use this button to rail out the reading first. So indeed, right now we're reading at 0 millivolts, so this rail function does work. That's actually comes in quite handy. So now let me dial it up at 1 millivolts. And you can see it is spot on. So let's do 2, 3, 4, 5, 6, 7, 8, 9, and let's dial 10 at a time. 10, 20, 30, 40, and you can see that is relatively accurate. 50, 60, 70, 80. Towards the higher end is a little bit off, but by reading the specifications, it is rated at plus minus 0.8 and plus 10 digits. So presumably that is still within the accuracy range. 90, 100. So not bad at all. So now let's take a look at the measurement for volt range. So for that, I'm going to change it to volts. And let's do it 1 volt at a time. 1, 2, 3. There's some range switching going on there. 2, let's do it again. 1, 2. Because it's a 20,000 count, so when we switch from 1.9992 to 3, you would expect losing 1 digit resolution here. 3, as you clearly saw just happened now. 4, 5, 6, 7, 8, 9, 10. So the measurement speed is reasonable. It appears it is at least twice per second, even though the range switching is a little bit slow. As you can see right now, we put the output enable, and it takes about 2 seconds to get to the final reading. So that's just something you need to be aware of. And let's take a quick look at the current measurement. For that, I'm going to change it to milliamp range. And let's see. Let's change this to DC current. Oh, that's kind of nice. So when you change it from the DC voltage measurement to current, it actually warns you to make sure that you're in the correct connection here, so that's good. Now let's take a look at the current measurement capability here. For that, I'm going to connect this with a 100 milliamp current source, and we'll see what we get here. So let's take a look, and it's roughly 100 milliamps. So just to verify that, I'm going to connect my unity meter and see if we get the same reading here. So let's see if we can read. Let me connect the unity meter instead. This is 100.25, so it's a little bit off, but nevertheless, it is measuring at no problem at all. So let's measure it again. 100.07. So the current reading is a little bit off, but if you look at the spec, it is the 200 milliamp range is spec'd at 0.8% plus 10 digit. So I think that is still within spec. Compared to the Handtech 2D72 we reviewed a while ago, this meter does have an advantage in its amp range measurement. As you can see that both the milliamp and the amp range are actually fused. So that gives you a lot of confidence when doing some high energy measurement. And right now I'm just going to give it a quick test. For that, I'm going to output a 10 amp current from my power supply here, and let's just give it a quick test to see whether or not we can measure that current. So let me enable the output. As you can see, it just goes shy of 10 amp. And when it exceeds that 10 amp range, yep, you will hear the warning that tells you that currently the current is in overrange. And now, of course, we can also measure resistors with this multimeter. So we can use this button to change it to the ohm range. And you can already see the range changes very slowly. And let's just short it out and see if you can see that for yourself. It takes a good 3-4 seconds for the range to come all the way down to the ohm range. So let's route it out. And let's just take a look at a precision 100 ohm resistor. Now this is going to be a little bit tricky as these leads are not gold plated, so we may have some fluctuation in our readings. So let's take a look. As you can see, as I move my leads, the readings are gradually changing, but eventually it does settle to the exact 100 ohm, which is not bad at all. Next, let's take a look at the continuity mode. And for that, I'm going to just short out the leads. I'm going to just short out the tip as these leads are not gold plated, so they may have some issues if you do the side here. So let's give it a quick test. So it is okay. It is definitely latched, but it is ever so slightly a little bit of sluggish. You can see that as I release these contact, you can still hear the buzzer continuing, but that is nevertheless adequate. And now let's take a look at the diode mode. For that, I'm going to start with a red LED to see if we can light it up and measure the forward voltage drop. So you can see that it did light up. You can probably see it. It's just very faint. And also measure the forward voltage drop, no problem at all. Now let's do it with a white LED. And we're able to light it up, but we're not able to measure the forward voltage drop, which is actually to be expected. Now, I don't think the battery life of this meter is as good as the 2D72 from Handtech I reviewed last time, as I played on and off for about 3-4 hours, and the battery is pretty much already drained, so I had to charge it up to continue shooting. And then when I do the teardown next time, I'm definitely going to measure the current consumption, so stay tuned. Now, one of the last ranges here is the capacitance measurement mode. So let me switch to that and we'll do some measurement. Now, the first capacitor I'm going to measure is a 22 picofarad capacitor. Let's see if we are able to measure that. It doesn't seem that it's registering. Now, if I short this lead, you'll see actually, when I short this, nothing happens either. So clearly, something is not quite right. with this capacitor measurement mode. That is interesting. So let me see if I short this. Huh. That is very unusual. So let me see if I can measure another capacitor. So the next capacitor I have here is a 100 nanofarad. This is a pretty standard, and I should be able to measure that. And you can see, yeah, we actually auto-ranged from 20 nanofarad to 200 nanofarad, and registered 72.5. I mean, it's in the ballpark, but I don't know if it is accurate enough. Hang on, so let me take out my Multimeter and do a comparison here. So again, this is the same 100 nanofarad. I will not bother zeroing it out as it's low enough here. So let's see. Yeah, okay, so it is actually accurate. So that one registered as a 74-ish, I think. So let's do it again. 70. Okay, so that is close enough. For whatever reason, we are not able to measure the 22 picofarad capacitor here. And I'm not sure if there's a one range down. And unfortunately, one thing I noticed is I cannot override a range. So for instance, if you are on DC voltage measurement or AC voltage measurement for that matter, you can use the range, manual range button to cycle through the different ranges you want the meter to be in. So therefore overriding the auto ranging capability here. And the same thing happens on some other ranges, I believe. For instance, if you're doing the ohm measurement, you can use the manual range. Let's see. Yep, I can manually range this through the 2 kilo ohm range, 20 kilo ohm range, and so on and so forth. So that's not a problem. However, when we are in this capacitance measurement mode, you can see that this manual ranging does not work. So anyway, now let's start measuring this capacitor here. That's a 15 microfarad capacitor. Let's see if we can measure the range here. So for that, I'm going to... Wow. Yeah, the reading is not what I expected. And sometimes it doesn't even measure. So it's all over the place. But you did see that the range switched automatically. Now I don't believe it's the leads that have some issue. Let me just swap them to make sure that the leads are actually, it's not what is causing the problem here. So let's switch it to the unity lead, and let's use a unity to measure this. So these leads are gold plated, so we can rule out the problem with the leads here. Nope. Definitely not doing what it's supposed to do. Huh. So actually it's very odd. Usually the capacitance measurement just works, but this one you can see that it is struggling. It's trying to register something, but it is not quite doing what it's doing here. And every time I measure it, it somehow returns a different capacitance. So let me try using the unity to do the measurement and see if we can get the correct results. And it could just be something wrong with the capacitor too, but I don't think so. So let me use unity to do the measurement here. Yeah, you can see that immediately measures 14.3, no problem. So clearly something is not quite right about the OWON capacitance measurement mode. And let me try it again. So now I swap the leads back. So let's see if we get any readings this time. Nope. And you can definitely see it's trying to measure something. And every time I measure, it returns different results. So clearly well, hang on. So now you can see that it actually measured the correct capacitance. So let's try it again. So I'm not sure why that is the case. So now it seems, nope, it's not measuring again. So it seems it's very sensitive to how the capacitor is measured. And so now let's try this other capacitor here. This one is a 1200 microfarad capacitor. Remember, this one can only measure up to 2000 microfarad. So this one is still within the range. So let's try it again. Yeah, again, we're struggling. So I think definitely there's something with the implementation of the capacitance measurement mode. And you can see that now it is measuring. So I don't know, if you have this meter and you can try in your capacitance mode, and let me know if you run into the same issue. Maybe it's just this specific meter, but I don't think so, because as you can see, clearly it is able to measure that capacitance. It's just very, very strict in terms of how you make the contact, and yeah, again, now it's not measuring correctly. So yeah, so definitely it's very finicky. Other than the last issue we saw with the capacitance measurement mode and a little bit of slow ranging for the ohm range, I will say that this multimeter actually is pretty good, especially considering it's just one of the three major functions inside this device. Also, I forgot to mention that the AC measurement on this meter is actually true RMS, so it's definitely a plus. Now I have hooked up the BNC cable from the arbitrary waveform generator output to the input of the first channel of the oscilloscope. So let's take a look at the functionality of this arbitrary waveform generator. And let me press the mode button, and we're in the waveform generator mode. So now I can press this button to enable it. So now I assume the output is actually enabled. So we can go back to the oscilloscope, and you can see that waveform is here. So let's use auto range to capture the signal here. I really like how fast the auto ranging works. And now you can see we have captured this signal with no problem. So let me get back to the waveform generation manual. And we can change the frequency using these buttons very intuitively. So for instance, if we wanted to change it to 1 megahertz, we can just go left here. And we make that digit a 1. And we turn down this last digit. So now we have 1 megahertz. And if you want to change different parameters, you can press this key to come down here. And again, you can change the different digit that you want to make a change to. For instance, if we want to increase the last digit to 1.01 volt, we can do that. And let's change it back. So that's pretty intuitive. Now we have a 1 megahertz sinusoidal signal. Let's go back and see how it looks on the scope. And we can require that signal here. Yeah, no problem at all. So let's go back, and this time, now I do wish we have dedicated buttons for different functions. For instance, one for DMM, one for oscilloscope, and one for signal generator, like what we saw in the Handheld 2D72. So it's a lot easier instead of having to cycle through every single time. But that's just something minor. So let's change it back, change the frequency, let's go up. Whoops, the frequency here. Let's change it back to 1 kilohertz. Now, of course, the implementation here is slightly different. You have to use this up and down arrow to get each specific digit. It's a little bit tricky to do sometimes. I do wish they have an on-screen keypad, like what we saw in the 2D72. Nevertheless, it's a different implementation, and it works just as well once you get used to it. So now we're back to the 1 kilohertz. We can change it to, let's say, square wave. And we'll go back, take a look at that waveform again. Yep, so that's our square wave waveform. Very clean, very nice. Now let's see what else we got. We also have ramp, so let's take a look at that one. Go back. Yep, that's our ramp signal. And you can see we can change the direction of the ramp by changing the symmetry here. So for example, if I change the symmetry down to 0, we will see the ramp the other way around. Yep. So that's not a problem. Now let's see what else we got. And we also have pulse. So the pulse, again, the duty cycle 50%, that's your square wave. So let's reduce that to, let's see, how low can we go? We can go to 1%. Okay, so let's take a look at our pulse signal. That is not bad at all. Next, let's take a look at the arbitrary waveform. For the arbitrary waveform, we can see that we do have quite a few built in. And you can see we have 6 pages here. So let's take a look at the first one that we are currently displaying, the staircase, which is the upstairs. So let's take a look. Yep, so that is no problem at all. It looks very clean and nice. Now, of course, we don't get to change the number of stairs that we're generating, and there's some limitations to what you can do in terms of controlling different parameters of these arbitrary waveforms. Nevertheless, you do have a lot of arbitrary waveform to select from. So, for instance, and one thing I found it very annoying is if I hit the wrong button, I have to cycle it through all over again. So now we're at arbitrary waveform. So let's go back to the staircase, and we can change it. Let's change it to, let's pick a different one. Let's do a sync function here. And you did notice it took a little bit of time to load that waveform into memory. But let's go back and see how that looks. Yep, no problem. Let's take a look at one more. And for this one, let's do a log. So let's go back to mode. Yep, as we can see, that is the waveform. Although there are plenty of arbitrary waveforms built in, there doesn't seem to be a way for you to upload your own arbitrary waveform design onto the device itself via the supplied software. At least I cannot find a way to do that, which is really a pity. And right now you see that the output is configured as high impedance mode. In fact, we can change that to match the 50 ohm impedance as well. And to do that is actually not that obvious. So what I had to do is first go to the system, and you will see that the load right now is high Z, and we can press it again, and now it changes to 50 ohms. So it shows up right here. So this is how you change the output impedance between 50 ohm and high impedance. Another thing that is lacking is that I found there is no modulation capability in this arbitrary waveform generator. As I combed through different menu options, I could not find anything other than just standard waveforms. And one last thing I want to comment on is the supplied software coming with this OWON oscilloscope. And that is a virtual oscilloscope you can install onto the computer, and it will just connect it via the USB HID driver. That actually worked without any hitch, but the functionality of that virtual oscilloscope is rather limited. There isn't really anything specific that you can do on the virtual oscilloscope you cannot do on this device itself. So in my opinion, that is not all that useful. And the USB can change from the human interface device to a mass storage device. So once you change it to MSC, it will show up on the computer as a drive, so you can transfer files between the OWON and your computer. And that pretty much concluded this review. All in all though, I really like the oscilloscope design in this OWON HDS272S. It is indeed a very capable handheld oscilloscope. The multimeter function is also a nice touch, especially given its 20,000 counts resolution, although the capacitance measurement mode seems to need some improvements. The arbitrary waveform generator also works like a treat, although it would be nice if we could upload our own arbitrary waveforms. But in general, I think the OWON HDS272S is quite an impressive device. I hope you enjoyed the video, and please remember to subscribe and give it a big thumbs up. I will catch up with you next time.